Water, the elixir of life. Water is an interesting molecule. It's not quite like the methane CH4 that we talked about in class. It has some different properties. Here's our learning targets. We should be able to list and explain the 4 properties of water that emerge as a result of its ability to form hydrogen bonds. Distinguish between the following sets of terms: hydrophobic, hydrophilic substances, a solute, a solvent, and a solution. Define acid, base, and pH. We're going to back off on solving most pH problems for now, and then explain how buffers work. Why are we studying water? Well, think about what life is made out of. It's mostly water. Think about a cell, all the cytoplasm with all the water. Cytosol is the fluid portion of a cell in the cytoplasm, and that's mostly water when you think about it. Plus all the stuff that's dissolved within that water. So the chemistry of water, interesting. We obviously have oxygen bonded to 2 hydrogens, and those are covalent bonds. This is the delta signal. That means this is a delta negative. We have delta positive. As we have mentioned, when oxygen bonds with hydrogen, they share a covalent bond. And in this case, it's not like methane. It's an unequal sharing. It's still a strong bond. It's still stable, but it's an unequal sharing. It turns out that oxygen is much more electronegative than hydrogen. Right? Remember this chart. Here's oxygen on the periodic table. It's right next to fluorine, meaning it's quite electronegative compared to hydrogen especially. It's not quite electronegative enough where it pulls away or steals those electrons completely, but it does cause some unequal sharing. When these electrons are circulating in between these 2 atoms, they're actually pulled towards the oxygen much more often than they are to the hydrogen. That's what these arrows mean here. So oxygen becomes a little bit more negative. It has a net negative charge. And hydrogen, because it spends less time with those electrons, it's said to have a net positive charge. So those are called poles, a negative pole and a positive pole. So we say water is a polar molecule, or it's a charged molecule, unlike methane, which is not. That was an equal sharing. There's no negative or positive poles with that one. So that's a nonpolar molecule, but water is a polar molecule. All right, that's going to cause it to have some certain behaviors. All right, first of all, water is sticky. So what makes it so sticky? What makes it want to stick to certain things? Well, it's because of the hydrogen bonds in between the molecules. Because hydrogen here is a little more positive than usual, it will be attracted to any of the other oxygens around it who are negative. So this one is attracting that oxygen right there. That's a hydrogen bond. When hydrogen bonds to a neighbor atom who has an opposite charge. It's a weak bond, but enough to want to make these molecules kind of stick together. Keep in mind the hydrogen and oxygen, that's part of its covalent bond, that stays together, but the hydrogen bond is between the molecules. So the covalent bond is within the atoms themselves, which makes the molecule. The hydrogen bond is between the molecules. So water tends to kind of hang out in little groups like this. Groups of 5. When you look at it, oxygen can be attracted to 2 neighboring hydrogens, and then a hydrogen attracted to a neighboring oxygen. So they hang out in little groups of 5, which makes them kind of sticky. They stick together. Water likes to stick to other water molecules because of the hydrogen bonds. All right, there's a closer look there. This is so extremely important in understanding how water works. We can also note, look at the shape of water. It kind of looks like Mickey Mouse. Because of the charges, the atoms bend a little bit like that, and it actually does look like Mickey Mouse. That's why we draw it that way. All right, so one of the properties, because of these hydrogen bonds in water, is cohesion. And cohesion, think of the prefix co, meaning together. The water molecules want to stick together. So if something is light enough, it can actually sit on top of those water molecules. And like this water strider is doing, you can actually see the water kind of dimpling underneath its feet or its legs, because those water molecules would rather stick together with their hydrogen bonds than let the little insect fall through. The insect isn't heavy enough to break those hydrogen bonds. Pretty cool. So that's the property called cohesion. The fact that water molecules stick together with hydrogen bonds, and then it creates kind of this sheet on top that these bugs can wheel around on, that's called surface tension. So surface tension is a result of cohesion, which is a result of the hydrogen bonds between water molecules. This also makes an impact with plants. Now, transpiration is how water moves up from the roots, up a plant's vessels, and then actually gets removed or poofed out from the leaves. Is that a good word, poofed? But it's what happens. So water moves from the ground into the roots, up the plant or the tree, and then out the leaves. It's actually a kind of important part of the water cycle as well, moving water around from liquid form to gas form. But how does the water actually move? One of the explanations for that is by cohesion. Water molecules like to stick to one another. There's that oxygen in red sticking to the hydrogen ahead of it, that's white, and they literally follow each other single file up these little vessels within the plant. It's called a vascular plant, meaning it has a network of vessels within. So it moves up and follows single file because of cohesion. Now there's another property called adhesion. Cohesion is when water molecules stick to one another. Adhesion is when water molecules like to form hydrogen bonds and stick to other substances, like the sides of these little vessels within a plant. So besides following one another due to cohesion, these molecules are sticking to the sides of these plant vessels, the vascular system, and then moving through those vessels, moving itself from the roots up to the leaves. It's conducting. You've heard of the word meniscus probably in your chemistry and physical science classes. Water likes to stick to glass. So when you have water in a graduated cylinder, remember how it likes to climb up the sides? And then it makes what's called the meniscus. And your chemistry teacher tells you, read the bottom of the meniscus when you're reading a graduated cylinder. Well, that's because of adhesion of water molecules. Capillary action, where water likes to move up little glass tubes or up little fibers of a paper towel as well. Water is also the solvent of life because of the fact of its charge or its polarity, because oxygen is the bully and it likes to spend more time with those electrons, and then it gives water its charge. It makes it a good solvent. When water has a charge, it's very much more able to get in between ionic substances and dissolve them. So think of sodium chloride with all its ions, its cations and anions. When water is added, the charged water molecules can move in between those ions based on the opposite charges. So the sodiums in sodium chloride get surrounded by the negative oxygens of water. The chlorines, who are negative here, get surrounded by the positive hydrogens of water. So water moves right in between all those ions and breaks them up and then dissolves them, which is awesome for our cells because there's some things in our cells that we want dissolved, we want in solution. So a solvent is something that can dissolve something else, and water is kind of a universal solvent. It doesn't dissolve everything, like it doesn't dissolve fat, but it sure does dissolve a lot of things. Here we have water surrounding a protein. And a protein is going to have certain amino acids that are going to have maybe a positive or negative charge, and water will be attracted to those areas, whether it's the negative oxygen or the positive hydrogen part, which can also help to get proteins dispersed within water. So here's some words for us. Things that like water or that are water loving are called hydrophilic things. They have an affinity for water. They mix well with water. So they are polar substances like sodium chloride, which is also ionic. Things that are hydrophobic. Phobic means it's a phobia. You don't like it. You try to get away from water. You do not have an affinity or a liking for water. Those things are nonpolar and they are non-ionic. So some good examples of that would be fat and butter. And this is a good thing that fat and lipids are not soluble in water, that they're hydrophobic, because that's what makes our cell membranes. And we don't want our cells to actually dissolve in water, now do we? We want them to hold their form. So it's kind of good that not all things dissolve in water, but a lot of things do. This is a basic construction of a fat here. If you notice, it has those wonderful, stable, and equal sharing carbons and hydrogens. And that's probably one of the reasons why it's nonpolar and there's no charges there. All right, so there's our properties of water. We have cohesion and adhesion, and then transpiration is a combination of both of those. The special case of ice. All right, Minnesota, this really counts, because at a certain temperature that Minnesotans can reach, that we reach here with our weather, water can freeze and become ice at 0 degrees Celsius or 32 Fahrenheit. So this could be detrimental because we are the land of 10,000 lakes, are we not? What if all of our lakes froze over completely in the winter? But luckily they don't. The top layer freezes, and that top layer, ice, floats. It's less dense than the water around it, which is very odd and rare compared to other substances where the solid form is usually more dense than the liquid form, and then it sinks. But because of the hydrogen bonds formed between water molecules, it's like those hydrogen bonds hold the water molecules at an arm's length and keep water that's frozen from getting too dense. And then it allows it to float on top of the liquid water when it freezes. All right, water reaches its greatest density at 4 degrees Celsius. It freezes at 0, and it's at a density that is less than the water around it because of those hydrogen bonds. Look at how much more spread out they are when they are ice versus when they're water and they're moving a little bit faster and unable to hold their distance. So our oceans and lakes don't freeze solid. If they did freeze solid, or if ice sank, that would not be good. We would completely lose all of the wildlife that lives in our water here in Minnesota. This also helps with the cycling of nutrients in a lake when our ice melts off the top in the springtime. And having that ice portion on top during the winter is like insulation for this little guy here who's under the ice. Look at him. He's still able to live under there and have water and go swimming, but he's got that ice on top that helps to insulate. So he doesn't want to get out. He needs to stay there. All right, here's some terms that I hope you're familiar with that might help for this next part. Kinetic energy. Remember, that's energy of motion when things are moving. So water molecules moving would have kinetic energy. Potential energy is energy of position, or like chemical energy. Like when you're sitting in a chair, you have potential energy because you could literally fall. And then when you would fall, it would turn to kinetic energy. Food has potential energy stored in its bonds for us. Heat is a measure of the total amount of kinetic energy due to molecular motion. The faster things move, the more heat, the hotter they feel. It's like when sun shines on your skin, it speeds up those molecules and they feel hotter. When it speeds them up too much, you get a burn. Temperature can measure this intensity of heat. All right, and we use Celsius scale usually when we're in biology, degrees centigrade. A calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. But the food packages where we read calories, they're actually kilocalories. 1 kilocalorie is 1,000 calories. Another unit of energy that we use is the joule. So if you want to know the conversion, 1 joule is 0.2 calories, or 1 calorie is 4.184 joules. So you'll see those every now and then. So here's a special thing, another special thing about water. Water has a lot of special things. Water has a high specific heat due to its hydrogen bonding. This basically means that those hydrogen bonds can kind of absorb some of that heat and resist changes in temperature. So having a lot of water on Earth and a lot of water in our bodies is kind of regulatory. It helps us to resist extreme temperature changes. This means it takes a lot more energy to heat water up or to cool it down. So we kind of stay nice and stable because of water with its hydrogen bonds. All right, so water on Earth helps to moderate our temperatures. Places where we don't have water, like in a desert, well, you know how that is. It gets extremely hot during the day and extremely cold at night. If there was some water there, that wouldn't happen. Humans like to live by water. Wherever we live by water, the temperature is regulated quite nicely. Look at San Diego, right next to the water, 72 degrees. Los Angeles, 75. Santa Barbara, 73. But go a little bit further inland, you're going to hit 106 in Palm Springs, where there's less water, therefore less moderation of the temperature. Water absorbs heat from the warmer air and releases stored heat to the cooler air. It helps moderate us. Water can absorb or release a large amount of heat with only a slight change to its own temperature. We like our water. So the specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change by 1 degree Celsius in temperature. So we use water as our standard as 1 calorie per gram per degree Celsius. And water, we say, at 1 has a high specific heat. That's important to life. Plus, on Earth, water can exist in all 3 phases. Water can be frozen, it's ice, and it can transition to liquid water, and it can also be water vapor. That's pretty neat. That's another interesting thing about water here on Earth. It helps us live. Water can be used for evaporative cooling. When water leaves your skin, it also takes heat away from you. That cools you down. In an organism like a dog who doesn't sweat, they do it over their tongue. They let the water evaporate from their tongue, which also takes away heat. Water can form ions, though. Once in a while, one molecule in every 554, at least in neutral water, will break away the H from the OH. If that's the case, then we have a hydrogen on the loose and we have a hydroxide on the loose. Hydrogens by themselves have a +1 charge and hydroxides have a negative charge. When you have these two components in water or in a solution equal, we say that that's a neutral pH. Down here, these brackets mean concentration of. When the concentration of hydrogen ions, though, is greater than the OHs, we say the water is acidic or the solution's acidic. So for instance, like in vinegar and orange juice, there's more H's running around than there are OHs. And then vice versa, if the concentration of hydroxide or OH groups is greater than the hydrogens, then your water is basic or alkaline. You have a base on your hands, like ammonia is a base. So how acidic or how basic a solution is determined on the pH scale. Though statistically rare, the dissociation of water molecules has a great effect on organisms, all right? So if a cell experiences a change in the concentration of H's or OH's, it could drastically affect the chemistry of that cell and even kill it, and even kill the organism. Here's my pH scale. I actually drew this myself, a scale of 0 to 14. 7 is neutral. So on a pH of 1 and 2 and 3, those are stronger acids. 5 and 6, not so strong because you're getting closer to neutral. pH of 8, 9, 10, you've got a base, not too bad, but when you get up here, like 12, 13, and 14, you have a really strong base, like drain cleaner, that's really strong base, might be a 13 or a 14. So the pH scale goes from 0 to 14 with 7 in the middle at neutral. Anything below 7 is acidic and has a lot of H's. Anything above 7 is a base and has a lot of OH's. pH is always based on the concentration of hydrogen ions. Like you see here, the concentration of, there's the brackets, the concentration of hydrogen ions determines the pH. So these numbers above the pH, these are the hydrogen ion concentrations. So at a pH of 1, your hydrogen ion concentration is 0.1. At a pH of 2, the hydrogen ion concentration is 0.01. A pH of 3, the hydrogen ion concentration is 0.001. You could fill in the rest of these if you like. Here it is at a pH of 12. Now you got to move that decimal place 12 places off to the left. All right, so the hydrogen ion concentration down here is high, but way over on the base side, there's more OHs, right? So it should be kind of common sense. If there's more OHs, we should have less H's. That's why the number of H's is 10 to the negative 12, why it's such a low number. Not to mean that that's safe. Bases can be just as dangerous as acids. You have to watch out. Okay, so this is our formula for that. The concentration of hydrogens times the concentration of hydroxides should equal always 10 to the negative 14. So that's kind of nice. If I know one number, then I know the other. The label is in moles here. In neutral water, this would be hydrogen ion concentration of 10 to the negative 7, and also a hydroxide ion concentration to the 10 to the negative 7. So then those 7 should add up to be negative 14, because that's how you add your exponents, right? Hopefully you learned that in math. All right, there's another representation of the pH scale and some common solutions that you can look for that would be at these different pHs, like gastric juice. Hydrochloric acid is way down at a negative, or at a 2, excuse me. That's why when you throw up, it burns, because that's so acidic. So many hydrogen ions. And lemon juice, why drinking lemon juice could wear away the enamel on your teeth. even vinegar, beer, wine, and cola, tomato juice. And then it's not so bad up here, but coffee is still a little bit acidic. Acid rain is about a 5 or a 6. Urine is about a 6. Pure water, like distilled water that's been purified, or human blood, most human tissues are at about a 7. Then we go the other way. Seawater is a little bit on the basic side. Milk of magnesia, you take that for diarrhea or constipation. That's kind of basic. Getting worse with the ammonia and the bleach, the oven cleaner, drain cleaner. Those are some nasty things. They have so many OHs. You should also note that every step on the pH scale is a 10-fold increase of or change in hydrogen ions. So a 10-fold change. That's why back here, when I was doing this, I was just moving my decimal place 1 for each step. So that's what makes it kind of nice and easy. You just got to move the decimal place. So acidic solutions are less than 7. Basic solutions are greater than 7. We want most biological fluids between 6 to 8, though some places that are closed off, like the stomach, could reach it too. And there's a part of your intestine that's kind of basic, but that's closed off, so that's okay. Each pH unit is a 10-fold difference in hydrogen ion concentrations. And even though it doesn't sound like much, a 10-fold difference is a lot, especially when we're talking living organisms and cells. That a 10-fold difference can mean the difference between a cell that lives and a cell that dies. So we have to be very careful. So we want most living cells to be about 7, unless you are maybe a member of domain Archaea and are adapted to living somewhere that's acidic or basic. We in our bodies have these molecules called buffers that help. So when there's extra hydrogens or extra hydroxide groups running around on their own causing trouble, we have these molecules who can grab onto them. They're called buffers. Here's an example of a buffer. HCO3 plus H. HCO3 can grab this loose H and then keep it tied up so that that H doesn't go cause trouble. So what is bad about having extra H's or OH's running around on their own? They tend to go and try to bond with proteins and enzymes and other molecules who are important and doing important jobs. And when they bond with them, they wreck their structure and then they can't work anymore. And so that's what can cause cell death or cause your proteins and enzymes to stop doing their job and stop making products or breaking down products that they're supposed to be doing, and so can be very detrimental to you. So good thing we have buffers to help us out. So the punchline is water is a polar molecule. Its special properties, which remember it all began with oxygen being more electronegative than the hydrogens and pulling the electrons towards them much more than the hydrogens. It started with that. It makes life on Earth possible. Then the chemical behavior of water can govern how organisms function. So 4 of our properties really to hit home here: the cohesive behavior, that those molecules like to stick to one another or even stick to other things. The ability to moderate temperature on Earth. Those hydrogen bonds kind of resist changes and they absorb some of the energy for us or resist giving up the energy. They expand upon freezing. It's like those little hydrogen bonds kind of push their arms out and hold the molecules of water at a distance. They do their social distancing. How's that? And they keep it from becoming more dense than the liquid around it. So it expands and then it floats. And then it's very versatile as a solvent. It can dissolve many things, which is good for our cells. The liquid inside the cells then can dissolve many substances like ionic substances, sodium chloride, and such. But it doesn't dissolve everything. Remember that. That's kind of important too, like cell membranes and fat. It won't dissolve those things. All right. So that is kind of a rundown then of Chapter 3 from your textbook. And so far, Chapter 2 was just your basic kind of chemistry rundown. Chapter 4 was carbon and those functional groups. And then Chapter 3, water, the elixir of life. Let me know if you have any questions about any of this.